Right, hello, my name is Hunter. I am a post-bac student at Portland State University, and this is our first week of content review for Principles of Biology students in Biology 211. So this is the week 4 topic. We'll be going over metabolism today, but before I do that, I want to get into just a couple of administrative items. Um, We'll be meeting live every Thursday at 3 p.m. You do not have to attend live. I'm currently speaking to an empty audience right now, which is fine. For those of you who join in live later or in the future, feel free to drop questions in the chat, and we can go through these worksheets together if you like. You can find these recordings on YouTube at the PSU Learning Center channel. I will be creating a playlist unique for this class that you can find there. You can also find recordings from past terms. So if you want to see it explained a few different ways, you can find a lot of the same content there. You are eligible for extra credit for submitting these worksheets. They're not going to be graded for correctness. They will be graded for completion, so make a good, honest effort. And that's all you got to do. Um, Show me that you can work through the exercise, and you will be eligible for those 2 points of extra credit for a submission. All of this content can be found on the Google Drive for the class. That should be included in an email that went out to each of you. And if you have any other questions, you can find me. My email, my contact information is up here at the top. Don't hesitate to reach out if you have any questions about content, about study habits. The tutors and workshop leaders and folks were super helpful for me when I was a principles biology student just 2 years ago, and I credit them with a lot of my success since then. So, week 4, metabolism. Let's go ahead and take a look at the exercises here. So, the question we're trying to answer is: do chemical reaction rates increase with increased temperature and concentration? We're given this study that was done based on the iodine clock, which is a really cool reaction. I don't know if you'll have an opportunity to do this in lab in your as part of your class, but I hope you do. It's very cool. So the question is, can the timing of the iodine clock reaction be changed? Our hypothesis is yes, chemical reaction rates increase as the number of collisions between reactants increase. An alternative hypothesis would be that chemical reaction rates do not change based on the frequency of reactant collisions. So how can we change the frequency of these collisions? Well, we can increase the concentration, the amount of dissolved solute in that solution, or we can increase the temperature, which is a measure of the average kinetic energy in the solution. So the experimental setup was they set up some reactants, they mixed those reactants with starch, and then recorded the time when the reaction is complete. And they did this at a variety of temperatures and at a variety of concentrations, with increasing concentration going this way, and it looks like increasing temperature going that way. So that's the experimental setup. And as the reaction completes, the solution turns dark, which is really neat. Oop. So the prediction of a hypothesis was the rate of the iodine clock reaction will be faster with increased concentration and temperature. And of course, we had our alternative here as well. And these are their results graphed out. So it looks like we have, anytime we look at a chart like this is a little science literacy for people who need a review. Always read the axes. We have our y-axis on the left and our x-axis on the bottom here. Sorry, my screen is being a little temperamental on my end. So your y-axis is vertical, x-axis is horizontal. Make sure you pay attention to what each of those axes are. So our y-axis in this case is the reaction rate in inverse time to completion. So that means as the number gets bigger, it's actually getting faster. That is really, really important to pay attention to. 1 over time. So if it takes 30 seconds, that is a much smaller number in this case than if it takes 1 second, would be higher up on that axis. So pay attention to your units. It'd be easy to make the mistake that it would be easy to make that mistake of higher numbers taking longer amounts of time, and that would make our alternative hypothesis true, which is not the case. So pay attention to those units. And then here we have temperature, and that one does increase linearly going up. And then we have our, again, reaction rate in inverse time and our concentration in units of molar or moles per liter. So just good to pay attention to those. So it looks like with our highest concentration, which they've nicely color-coded in this darkest orange for us, we have the highest bar here, which again, looks like 1 over 10, is this seconds or minutes? It doesn't actually say. So 1 over 10t, which would be 1/10 the amount of time that this one took at the lowest concentration. So all good things to be aware of here. And so in conclusion, it looks like the rates of chemical reactions did increase as the number of collisions between reactants increased, such as when the concentration or temperature of the reactants increased. So having taken a look at that now, I really wish I could get rid of these little Grammarly bubbles. I will fix that before the next stream, I hope. Now that we've taken a look at that, we get to create our own experiments looking at this. So the figure above shows data from an experiment designed to determine if chemical reaction rates increase with increased temperature and concentration. Students at Parkland College tested the effects of temperature and concentration on reaction rates separately, and the results are shown here. You are a lab technician at a biotech company and need to determine the fastest way to make large quantities of HSO negative. How would you design an experiment to test the combined effects of temperature components on your experimental design, controls, replicates, and concentration, and temperatures of reactants? Clearly state your predicted and null hypotheses and draw a graph of your expected results. There are obviously a lot of ways that you could answer this question. So I'll give you one version that would be a good example here. So let's say, I can probably type this. Give it a shot. Nope. I have no idea where that typed. There we go. So let's make a prediction. We're talking about kinetic energy. We're talking about rates of reaction here. So let's say that the chemical reaction rates will increase with increased temp and concentration of reactants to a certain point, where the reaction rate will level off. Just making a best guess here. The null hypothesis, of course, would be that the reaction rates are not affected by increases in temp or concentration of reactants. So to best understand those two, we then have to run an experiment looking at the combined effects, but first testing each of those individually. So let's see here. How do I want to say this? First, like the experiment above, we should really look at what impact temperature and concentration have on their own, and then that gives us a baseline for each of those, and then combine those effects. Let me see here. So our expected result, we have reaction rate on the y-axis, and on the x-axis here we can have temp. And we would have another one, of course, for concentration. And we might have one trial that looks something like this, and another that has something like this. And then purple would be our fastest as we increase temperature the highest, we will say. Yeah, something like that. And then similar story. We could have a graph that looks something like that, with our minimum 3 trials for each of those. And that would give us our baseline. So to test the combined effect of temperature and concentration, the 3 concentration levels could then be tested at each of, say, 5-degree temperature increments. And so you would have, I'll just edit this one. So you'd have concentration 1, concentration 2, and then another one for concentration 3 at, excuse me, no, you wouldn't want to edit it that way. You would have concentration 1 up here and temp, and then concentration 2 and temp. And let's say that concentration 2 is a lot higher and you did it at those various temps. Maybe it has a steeper slope to it. And that would give you the impression that increased concentration and temperature together had a great effect. And if our hypothesis was correct, we would have a third concentration that was somewhere in the middle. Right? We had concentration 1 and concentration 2 on either side. Concentration 3 was a leveling off point where basically you added more stuff, but it didn't have a greater impact than, let's see, if the concentration of solution 3 was greater than the concentration of solution 2, but solution 2 activated faster, then concentration 2 may be closer to the saturation point. That's the most solute that it could handle and still have, you know, a fast reaction. So really, that would probably line up exactly the same if we're talking about reaction rates relative to concentration and temperature. So that's one example. Show your expected results basically and talk about how you would set up your experiment. And really think through this. I think designing these experiments is a really good way to understand how researchers get to where they do. What can you reasonably say based on the way you set up your experiment? What are your controls? What are your variables? So, alrighty, so let's do a quick review of energy transformations. To maintain life, organisms must be able to convert energy from one form to another. For example, in the process of photosynthesis, algae, plants, and photosynthetic prokaryotes that use the energy from sunlight to convert carbon dioxide and water to glucose and oxygen, which are effectively waste products. So summary for the reaction of photosynthesis can be written below. You have, this is one of those things that is going to come up over and over and over again in your biology education. If you memorize an equation, this is a good one. This is the balanced equation of 6 units of CO2, 6 equivalents of CO2 plus 6 equivalents of H2O or water transitions to C6H12O6, which is glucose, and 6 equivalents of O2, which is molecular oxygen. This type of reaction is an oxidation reduction or redox reaction. And this reaction is also, is it anabolic or catabolic, or endergonic or exergonic? So an easy way to think about this, or an easy way to remember it, anabolic means you are building something up, you are building up molecules, and catabolic means you are tearing it down. The way that I was taught to remember it was if you've ever had cats at home, cats can be a little bit destructive, and so that's breaking down molecules. This is the conversion of CO2 to H2O is a anabolic reaction. We are building a larger molecule, glucose, from smaller constituents. And this is an endergonic reaction. So focus on these prefixes, ender versus exer. Exergonic, like exit, means out. The prefix ender would be coming in. So energy is going into the reaction to build this larger molecule. Typically, when you break apart molecules, energy is released. And this is something that you will be repeated ad nauseum as you go on in your, especially chemistry education, as a fundamental law of the universe. So in redox reactions, electrons and the associated H+, these are protons, hydrogen ions, are transferred from one compound or element to another. If one compound or element loses electrons and becomes oxidized, another must gain electrons and become reduced. So reduction is gained. It sounds backwards, but it'll make sense later, I promise. Oxidation is loss, reduction is gain. Oxidation is loss, reduction is gain. Handy little mnemonic here if you need help remembering it. Let's see, for example, in photosynthesis, water becomes, is it built up or broken down? Oxidized or reduced? Does it gain electrons or does it lose electrons? In this case, water becomes oxidized to O2, and the electrons and associated protons it loses in the process reduce CO2 to form glucose. So keeping track of where electrons and charges go will get easier with practice. So trust the process there. Alrighty. Do anabolic or catabolic reactions build more complex molecules? Anabolic. Whoa. My screen again. Hello. Anabolic reactions build more complex molecules from simpler ones, and to do this, they require an energy input. Reactions that require the input of energy are termed endergonic. Ender meaning in, exer meaning out. The reactions involved in aerobic respiration are also redox reactions. And this is another one that is going to show up over and over again in your education. I'm taking anatomy and physiology right now, and we just did this unit again. So you will see it in biochemistry. You will see this a lot. So in this set of reactions, however, a more complex molecule is broken down into a simpler one. Glucose, which should look familiar from the equation above, glucose is broken down or becomes oxidized to CO2, and the oxygen becomes reduced to, the oxygen becomes oxidized to water. Yeah, because we're building up a larger molecule. Breaking down, This might be, sorry, this is, we'll see it over and over again, and I still make mistakes. Glucose is broken down or becomes oxidized, yes, to CO2. And the oxygen becomes oxidized or reduced. Oxidation is lost. I think it's oxidized. I think it's oxidized. I will triple check that. We will come back to it. All right. So which reaction breaks down more complex molecules into simpler ones and in the process release energy? Catabolic. Reactions that release energy that can be used to do work are exergonic. They release energy to do work. Therefore, aerobic respiration is a catabolic process, breaks down molecules process, and it is exergonic. Cool. So starting to see, this is just a good exercise to get in the practice of thinking about which direction energy is going. Is it building up or breaking down? And getting comfortable with the vocabulary of oxidation, reduction, anabolism, catabolism, or anabolic, catabolic. Alrighty. which reactions are also said to be spontaneous reactions. So you will later learn about Gibbs free energy, which is a measurement of energy available in the universe and in these processes. Exergonic reactions are said to happen spontaneously. Now, does this mean that it won't keep? Does this mean that if we don't keep glucose in tightly sealed containers, it will spontaneously interact with atmospheric oxygen and turn into carbon dioxide and water? The answer is obviously no. Excuse me. Um, Spontaneous reactions rarely occur spontaneously because all chemical reactions, even those that release energy, require some addition of energy, the energy of activation, before they can occur. And that energy of activation, if we're looking at a chart, so reaction progress and energy on our vertical axis, you'll have something like this. And this margin in blue that I've just drawn on, this is your activation energy. So that's the amount of energy input required to get the reaction to move forward and release more energy, as is the case in this particular graph. They can look very different. So let's see. Spontaneous reactions rarely occur spontaneously because all chemical reactions, even those that release energy, require some addition of energy, the energy of activation, before they can occur. One way of supplying this energy is to add heat. An example is heating a marshmallow over a flame or campfire, and when enough heat is added to reach or overcome the activation energy, the sugar in the marshmallow reacts by oxidizing. Burning is a form of oxidation. So if you've ever seen the SDS signs or the safety signs on chemical containers, and it says oxidizing agent, it's probably highly flammable. Not probably, it is. The marshmallow will continue to burn even if you remove it from the campfire, and as the marshmallow burns, carbon dioxide and water are formed as products of the reaction, and the energy that was stored in the bonds of the sugar is released as heat. So if our cells used heat to overcome activation energies in metabolism, they would probably burn up like the marshmallow did. Instead, living systems use protein catalysis or enzymes to lower the energy of activation without adding heat. And in addition, the metabolic breakdown of sugars is carried out in a controlled series of reactions, and at each step or reaction in the sequence, a small amount of the total energy is released. Some of this energy is still lost as heat. The rest is converted to other forms that can be used in the cell to drive or fuel coupled endergonic reactions or to make ATP. And that coupled reactions is really important. ATP and the energy that it releases is a coupled reaction. So that the reaction of breaking apart the ATP is coupled with something else to drive the reaction forward. ATP being that currency of the cell. So this was a short and sweet worksheet, little workout for the old cerebral cortex. We're only 24 minutes in, so I do see a couple people are here live in the chat. Feel free to type and say hello if you have questions. Feel free to ask them. I'll hang out for a couple more minutes, but that's all I have for you for today. Do remember to turn in your worksheets on time. Late submissions will not be accepted. Worksheets are due by 5 p.m. on Friday, the week that they are presented. So the best way to show up to these things is to have downloaded the worksheets early in the week, taken a look at them, worked through some of the stuff, and then at the session on, I guess it's Thursday, at our session on Thursday, review the recording, make adjustments to your worksheet or not, that's fine, but go through your completed worksheet and correct things, work through the ones that you couldn't get to, and do make sure that you submit. Again, you're not going to be graded on correctness. That is for your own benefit. You will get that extra credit either way for having done the exercise. So, am I forgetting anything? think that's all I've got. So if anything else comes up, let's see. So we all need to do is create an experiment. Yeah. So to get the most out of this exercise, you can take a look at the experiment that was created, take a look at the prompt, and then, yeah, design an experiment. Think through what factors you want to test, how you want to test it, how do you establish your controls, things like that. And write down your predicted hypothesis and what your results should look like if your hypothesis were correct. So, does that answer your question? Also, thanks for chiming in. No, you are not expected to actually run the test. I'm pretty sure that HSO is a pretty volatile compound. It would be pretty dangerous to handle, I think. So no, definitely don't do that. But this is just going through the thought exercise and thinking about if you wanted to figure out how to make a ton of this thing, how would you test the different conditions? Um, so yeah. Um, and also that would be a crazy amount of work. Let's say it was realistic to do this experiment. Um, you are so welcome. Let's say it was realistic to do this experiment. That would be a huge expectation to saddle you guys with for a couple of extra credit points. So don't sweat it. Um, on that note, if this is something that you just do not have time for, maybe you work a full-time job or you have people that you need to take care of, focus on the rest of your class first. Make sure you're getting good grades on those homework assignments. Make sure that you're focusing on preparing for your exams. Ideally, this is another way or an effective way to prepare for your exams that also gives you a little extra credit. So trying to think about how to game that system a little bit because unfortunately we are playing for points. Um, it is it is important that you get the material and that you understand it, but it is also equally important that you be able to show that knowledge that you've acquired in the form of taking these tests. So and that was something that I had a really hard time with coming back to school. I had really intense testing anxiety, and getting some new testing strategies was really, really helpful for me. So, and again, my information is included in the info folder that you all should have a link to. Feel free to reach out if you have questions. I will make myself as available as I can while also prioritizing my own studies. With that, I'm going to let you all reclaim some time. Enjoy the rest of your Thursday evening. I understand you may have some exams coming up soon if you haven't taken them already. So good luck. Take some deep breaths. And I'll talk to you all next week.